The title of this lecture is Swapping Policy. The goal of a victim selection is to minimize number of cache misses, which is equivalent to the minimized number of disk accesses. We first introduced the term average memory access time, AMAT, and we define four variables: probability that given request is served by memory, and probability of PMIS is the probability that given request is served by the subspace. And then TM is time to access memory, and TD is time to access disk. So AMAT is weighted sum between the time to access memory and time to access disk. The first approach is the optimal replacement policy. Optimal replacement policy is actually impossible to implement because we need to know the future, and it is impossible to know the future. Overall, the optimal replacement policy is used as a baseline metric for how good the proposed heuristic is. So optimal replacement policy lead to the fewest number of misses overall, and the basic idea is replace the page that will be accessed furthest in the future. So the optimal replacement policy result in the fewest possible cache misses. Let's examine how optimal policy changes the contents of the physical page frame. Assume that there are 3 page frames in the system. This is a reference string, and reference goes this direction. So initially, all 3-page physical frame is empty. So first 3 accesses going to result in miss. And then because there are 0, 1, 2, so accessing page 0 result in hit, accessing 1 result in hit. And then when we make a request for 3, there is no 3 here. So we have to select one of 0, 1, 2 as victim. So 0 is going to be accessed next, and 1 is going to be accessed and third. So we have to select 2 as victim and replace it. So as a result of kicking 2 out, the contents will going to be 0, 1, and 3. Then next 2 accesses, page 0 and page 3, and page 1 is going to be hit. And then after making a request to page 2, there is no page 2 here, so we have to select one of the 3 as the victim. Because 1 is going to be accessed next, so we have to choose either 0 or 3 as victim. It doesn't matter which one we choose. So anyway, if we decide to choose page 3 as victim, then after make a request for accessing page 3, the page frame is going to include page 0, page 1, and page 2. So out of 11 accesses, there were 6 hits. So hit rate is 54%, 54.6%. And of course, in this policy, we assume that we know that what is going to be accessed in the future, but that is not possible. The simplest policy is FIFO. Operating system places the page in the queue when they enter the system, and when an operating system needs to replace one of the pages, it replaces the page that is tail on the queue, which is the page that has been brought into memory for the first time. So it is very simple to implement, but it can't determine the importance of the blocks. Let's provide an example. Again, the same reference string from here to here, and then it goes down this direction. So first 3 accesses result in misses. So after 3 misses, the contents of the page frame will look like this. It will contain page 0, page 1, and page 2. And next 2 accesses will be hit again. And then when we make a request for page 3, there's no page 3 in the page frame, so we have to kick out one of the 3, page 0, page 1, and page 2. And because page 0 has been brought into memory at the earliest, so we kick that out. Then, after making a request for page 3, the contents of the page frame is going to be page number 1, page number 2, and page number 3. Then the application asks for page number 0, but because there's no page number 0, it results in miss. And then the next page to kick out is page number 1 because it has been brought into memory earliest among the 3 pages, page 1, page 2, and page 3. So contents of the page becomes page 2, page 3, and page 0. Next, application asks for page 3, and it is already in memory, so it's going to be hit. That's lucky. And then we ask for page 1. However, among page 2, page 3, and page 0, there's no page 1, so we have to kick one of those out. Page 2 has been brought into memory at this point, and page 3 has been brought into memory here, and page 0 has been brought into memory just before. So we have to kick page 2 out. Now, there's miss, and then now page frame contains page 3, page 0, and page 1. And then when you make a request for page 2, it results in miss again. So we have to kick out one of page 3, page 0, and page 1. And page 3 has been brought into memory at the earliest among the 3. So we kick out page 3. And then contents of the memory become page 0, page 1, and page 2. And the next request for page 1 becomes hit. So, well, there are not many hits. So there are 1, 2, 3, and 4. So out of 11, there were only 4 hits. So hit rate is 36.4%. So the hit rate is much lower in FIFO than in optimal policy. And there is another interesting mechanism in FIFO policy. This phenomenon has been found by a scientist, Beladi, and is called Beladi's anomaly. Most people expect that if they purchase more DRAM and put it into memory, then that's going to be result in the lower cache miss rate. That's normal expectation. But Beladi has found that that does not hold for FIFO policy. So in FIFO, even though you put more memory, the cache miss rate can actually goes up. This is what we see, what he has observed in his experiment. So in this reference string, when there is page frame number is 3, then page fault, there are 9 page fault. However, if you increase the page number of page frames from 3 to 4, then the page fault count increases from 9 to 10. So this is a well-known result of Beladi, and it is called Beladi's anomaly. Another simple policy is random. It is not FIFO, it is not optimal, and it is just random. It picks up the random page to replace under memory pressure. So it does not really try to be too intelligent in picking which blocks to evict. So it's just random. It's randomly choose the victim. But if you look at here, then out of 11 accesses, there are 1, 2, 3, 4, and 5. So the hit rate is nearly 50%. In the previous page, FIFO, the hit rate is 36%. So it's much better. It's much better not to do anything in this situation. So okay. So sometimes random policy is as good as optimal. Next approach is using the approach that uses history. So to select a victim, we learn from the past and use it to select a victim. So there are 2 types of approaches in history-based information. First one is recency information, and then second one is frequency information. In recency-based approach, the more recently a page has been accessed, the more it likely will be accessed again. So that is basically a selection policy of this approach, recency-based approach. And the name of this approach is called LRU, least recently used. And another philosophy, another approach is if a page has been accessed many times, it should not be replaced as it clearly has some value. So which is based upon frequency. That approach is called least frequently used. Let's do some example with least recently used approach. The reference string goes from left to right, and this table from top to bottom shows the changes in the page frame contents in our example. So there are 3 misses at the beginning because all 3 physical frame is empty. And then there's page 01. This is hit because it's here. The second request for page number 1 is hit because it's here. And for the request for page number 3, there's no page number 3 here. However, so we have, in kicking out one of the 3 pages, it kicks out the page that has been least recently used. So page 1 has been accessed just before, and page 0 has been accessed also just before. So we have to kick out page number 2 and then put it here. So if you look at the contents, then the order here brings some value. So if the page is placed on the right hand side, it means that it has been accessed more recently. When we access page 0, okay, then page 0 is accessed. So the position of page 0 is shifted from left to right. Again, if page 3 is accessed, then the position of page 3 is moved to the rightmost position. And if page 1 is accessed, and page 1 is shifted to the rightmost position. And then when you access page 2, it is not included in the current page frames. So it kicks out one of the pages. In least recently used policy, it kicks out the least recently page, and which is page number 0 here. And then in access page 1, then page 1 is accessed and moved to the rightmost position. So if you count the number of hits, then there is 1, 2, 3, 4, 5, 6. So we have 6 hits out of 11 accesses. This is the same as optimal replacement policy, which is good. We like to examine the relationship between the amount of DRAM in the system and then associated page fault rate. The important rule is that if you can put entire set of pages in memory, the policy doesn't matter. Replacement policy matters only when you do not have sufficient memory and have to select victim for a page replacement. Most workload exhibits some type of locality. If locality means when a page is accessed, the page gets accessed multiple times. That's what we call temporal locality. When a page is accessed, its neighbor pages are accessed thereafter. That's what we call spatial locality. So victim selection algorithm has to exploit this type of locality features to minimize the page fault rate. However, if the application accesses the pages just at random, there is not much things to exploit to reduce the page fault rate. Here you see the graph. The x-axis is cache size, it's size of DRAM. Then y-axis is hit rate. If we put entire set of pages, because there are this application accesses 100 unique pages over time, and then the cache size is the same as the amount of pages it's accessed, then hit rate is 100%. That's for sure. However, our objective is put a small amount of memory and remove improve the page fault rate or hit rate significantly. That's what we would like to achieve. For example, from here to here, we increases the page DRAM size, from 20 to 40, and then we observe a significant fraction of page fault increase, improve page fault. Okay, but if an application accesses the pages in just random, there's not much things to exploit. So unless we know the future precisely, for random workload, no policy can really help. This is 80/20 workload. This workload exhibits a strong locality. In 80/20 workload, 80% of references are made to 20% of the page. And then remaining 20% references are made to the remaining 80% of the page. In that case, the workload shows strong locality. In that case, even though we add, let's look at the example. Let's say there are a small amount of page physical DRAM, and at that point, the page hit rate is roughly 30%. But if you increase the physical block size from here to 20, then we can reach almost 80% hit rate. Okay, so we observe a significant increase in the hit rate by putting some small amount of memory here. But after we reach this point, even though we double the size of the physical memory, we only get very small amount of memory increase here. So if you, in that case, for example, for the size of page frame number 20, if you can compare different page replacement algorithms such as OPT, least recently used, and FIFO, and random, and OPT of course yields the best policy, but LRU yields the best policy among the heuristics. Another interesting workload is looping sequential. In this workload, application refers to the 50 pages in sequence. So it starts from page 0 and then sequentially access those pages from 0 to 1, 3, 2, 3, 4, 5, 6, and then until page 59. And then after it accesses page 49, it goes back to page 0 and then do the same thing again. And we repeat this sequence for a total of 10,000 accesses. Because there are only 50 pages, if you put 50 pages, then there's going to be 100% cache hit rate, 50. But before then, for looping sequential, OPT, the hit rate increases linearly with the cache size, but for other workload, other victim selection policies such as RU, FIFO, and RAND, it does not work well. There is an approach that approximates least recently used page replacement algorithm, which is called clock. We need a use bit, a special bit, and it's a hardware. Whenever a page is referenced, the use bit is set by hardware to 1. Every time a page is referenced, the use bit is set by the hardware to 1. And hardware never clears the bit. Operating system periodically resets the bit to 0. Then how is this bit used? In clock algorithm, there is a clock hand here. And all pages in the system are arranged in a circular list. And clock hand points to some particular page to begin with. And the algorithm continues until it finds a use bit that is set to 0. And if it finds a bit that is set to 0, then it selects it as a victim. And if a use bit is 1, then it clears the use bit and advances the hand. This is how the clock replacement algorithm works. Despite its simplicity, a clock algorithm works very well. Of course, this is 80/20 workload, and this is optimal policy. The clock algorithm works as good as LRU, so it successfully achieves its objective of approximating the behavior of LRU. And of course, it does much better than approach that does not consider the history at all. When we select a victim, we can also consider whether a page is dirty or not. And hardware includes a modified bit. It is known also as a dirty bit. And if the page is modified after it is brought into memory, then the bit is set and it's called dirty. So when operating system replaces this page, it must be written back to the disk to effect it. Clean page is different. When we replace the clean page, the eviction is basically free. You can simply overwrite the existing page. So when you select victim, you can check whether if the page is dirty or not. There are a number of ways to minimize the disk I/O from disk to memory or to disk from memory, and one of the approaches is prefetching. When you brought into memory, operating system brings not only the requested pages but also the other pages that is nearby the requested memory. That's because of the spatial locality. So when you are going to brought the page 1 into memory, you does not only bring page 1 but also page 2 together, or page 3 and page 4. Because if you know that page 1 has been accessed, then it is likely that page 2 soon be accessed. So it's because accessing a disk is very expensive, you may want to bring those 2 pages at the same time to minimize the disk access time. Of course, everybody can make mistake. So even though you brought a page that has not been requested, but because it is situated, it's located nearby the request page, you may want to bring it. But it is possible that you may bring the wrong page. And when you write a set of pages to the disk, instead of writing them one at a time, you may want to collect a number of pending writes together in memory and write them to the disk as a single write. So it is called clustering or grouping. The operating system increases the degree of multi-programming to increase CPU utilization. Let's assume this situation. There are 10 physical page frames in the system. There are 10. And then each program requires just about 3 pages for it to run. So the operating system puts one program, and then CPU utilization is about here. And then it keeps increasing the number of programs it wants to execute in memory. And then as it brings more memory at the beginning, the CPU utilization increases because there's more programs to run. So 1 program, 2 programs in the system, and 3 programs in the system. However, each requires 3 page frames, right? So whenever operating system brings 4 programs in its memory, then the total number of required page frames is going to be 12, which is much larger than 10. If this happens, then every execution of a program results in page fault, and it triggers victim selection, and it swaps out the existing pages. So in that case, memory is oversubscribed, and the memory demands of the set of running program exceeds the available physical memory. And then suddenly, the CPU utilization substantially drops, and program behavior slows down substantially. That's what we call thrashing. So, operating system has to make sure that there are sufficient amount of physical frames in the system to run a set of given processes. In summary, in this lecture, we covered what the swapping is, and then we covered basic page replacement algorithms such as RRU, RFU, random, and FIFO. And also, we have covered the approximation algorithm to LLU, which is called clock, and we show that the clock algorithm works nearly as good as the original form of RRU. And to make the IOs more efficient, we have to make the IO size larger. There are two approaches. First one is clustering and grouping. When you write a set of blocks to the disk, we cluster multiple blocks together and write it as a single unit. The other one is prefetching. When you when you bring in a page, we not only bring in the just request page, but also bring in the other neighbor pages of the given request.